Hello everyone. So let us continue our discussion. We are in week 11 and this is our fifth lecture. So let us continue solving some more problem. Our first example today is a beam which is a cantilever and it has a UDL over the entire length. So this is omega. Now at the free end, we have a spring. And the spring constant is K. So the task is to find out the reaction at the end B. Okay. Earlier we solved a similar problem where we had a prop at the end B and we solved that problem, right? If you recall in the previous lecture, right? Now here we have a spring instead of a support. So obviously there will be some deformation. Now you can imagine if there is no spring and we allow the beam to deflect, obviously it will deflect at the free end due to this UDL and this is the delta. Now we can also imagine that the spring here is getting some force say P, and that force is acting here. So now if we consider the first structure and then find out the strain energy, then we can also consider the second structure, which is a spring. So the first structure is the beam and the second structure is the spring. Now for this first structure, let us first find out the moment at a distance x. So consider 1. So we have mx is equal to p of x. So this is p minus omega x square divided by 2. So the bending straining energy UB1 is equal to 0 to L, length of the beam is L and flexural rigidity is EI. We have mx square dx divided by twice EI. So we have 0 to L, in place of mx we have px minus omega x square by 2 whole square dx divided by twice here. Now if we differentiate this strain energy with respect to P, we get delta B. And for that we have 0 to L P of x minus omega x square divided by 2, that multiplied by x dx and divided by EI. So we have 1 by EI and then integral of px times x, so px square. So for that we have px cube by 3 minus the second term is omega x square by 2 times x, so omega x cube by 2. So we have omega x to the power 4 divided by 8 and evaluated over 0 to L. So we have 1 by EI and then within bracket PL cube divided by 3 minus omega L to the power 4 divided by 8. Okay. Now consider the second component, right? Now in this second component, we have a spring which has a constant K and it is also experiencing a deformation delta B. Now for this spring, if we find out the strain energy, it is half the load, that is K times delta B times the displacement delta B. So we have K times delta B is P, so P by 2 into delta B, and we know delta B is equal to P by K. So now we can write P square by twice K. So if we differentiate this second strain energy with respect to P, we get P by K, and that is delta B. Now if we equate this to, what we have is P by K plus the other part 1 by EI within bracket PL cube by 3 minus omega L to the power 4 by 8. So we have 1 by EI PL cube divided by 3 minus omega L to the power 4 by 8. This is equal to 0. So what we can do, simplify this quantity. So P by K plus PL cube divided by thrice EI is equal to omega L to the power 4 divided by 8 EI. So we get P is equal to omega L to the power 4 divided by 8 EI and then 1 by K plus L cube by thrice EI. So if we simplify it further, we get thrice K omega L to the power 4 divided by 8 times 3 EI plus K L cube. So that is the reaction we have when the free end B is supported by this spring whose constant is K. So again, in this case, you see how we can use the theorem of Castigliano to solve the problem, right? Now we'll take a different problem. We can solve truss, an indeterminate truss, using theorem of Castigliano. Let us see how we can solve this problem. So we have a truss here, and let us mark the ends. So we have A, B, C, and D. So this is our example 2 today. And the length of the sides are L and L. And we have two forces at the point D. One is horizontal of magnitude P and another one is vertical. Now we have two supports, and for that, if you recall, capital N is equal to M minus 2J plus 3. So this is for 2D problem. This 3 is the number of external equilibrium equations we have for this 2D problem. Now this J is number of joints, right? And M is number of members. So in our case, we have altogether 6 members and 4 joints, right? So if you put that in this expression, what we get is capital N is equal to 6, that is the number of members, minus 2 times 4, that is the number of joints, plus 3, which is equal to 1. So we have internal indeterminacy of 1, right? And in fact, you can easily check that if we remove one member, as you can see here, then we can solve this truss, right? So we have a vertical force here P and a horizontal force here P. Now, this second truss where the member DB is removed, the DB is here. This truss we can solve. In fact, we'll solve this truss in a minute because the internal indeterminacy is removed. Now just imagine we have a member force which is F. So we apply a member force F, and that F is unknown. So what we'll do, we'll solve this using Castigliano. Let us see how we can solve it. And obviously that member force is applied here. So this is F, and here also we apply the same force. Now, from the dimension, we can find out the length of the members dB, right? And we can also find out the strain energy stored in this member, and that is F square. F is the unknown member force times L BD divided by twice AE. Now, this is the strain energy stored in these members. Let us just mark the members. So we have 1, 2, 3, 4, 5, and 6. We have removed that 6th member, and the moment we remove it, it becomes determinant, and we replace that with a member force F, which will solve. Now for this structure, we can find out the strain energy stored within the structure, and if we differentiate that with respect to F, we get the deformation along the line of action of the force, which is F here, right? And that will be exactly same if we differentiate this quantity with respect to F. So the displacement of the member is, say this is the member 6. So U6, if we differentiate with respect to F, is delta of F. And this we can write, it is F L dB divided by AE. Right. So this is U6. Now for the remaining truss, we can find out the strain energy stored, right? So if we do that, we have the total strain energy stored in the structure is summation of all Ui, I ranging from 1 to 5. Now let the member forces are Ri, so Ri square times Li divided by twice AE is the strain energy stored in the ith member, and let us sum it up between 1 to 5. Then we get the total strain energy stored in this structure. Now obviously, if we differentiate ut with respect to the unknown force F, then what we get? We get delta F, right? So in other words, we can write this is equal to minus F L dB divided by AE. So this is equal to differentiate U6 with respect to F. Now, if we take this on the left hand side, what we have summation of Ui, I ranging from 1 to 6, because this is the sixth member that we have removed, right, is equal to 0. Right? And that satisfies the condition at the end B and D, because we have the member here and the displacement in the member dB will be exactly same what we have here the moment we differentiate the strain energy stored in this determinate structure with respect to F. Effectively what we have, you see here, we have strain energy summed up from 1 to 6. So we have all the 6 members for this indeterminate structure, and that we differentiate with respect to F. F is the member force which is unknown, that we are going to solve this member force, and with respect to that member force, if we differentiate total strain energy, we get 0, right? So let us solve this structure. So for that, let us consider the second structure where we remove the member and apply a member force F. Now we have a reaction here, a reaction there, a reaction here. We'll solve all these reactions in a minute. So we have A, B, C, D. Now if you start from this end, we can easily solve the member forces for this structure. So if you consider say point B and apply method of joints, you can identify the member forces, right? So this member force is P plus F by root 2. Now, if we come to this member AB, we can identify the direction of this member force. So, if you resolve this F along horizontal direction, that will be balanced by this member force AB, and this member force is F by root 2. Next, if we come to the point C, we can identify the direction of the member force AC, and we can also solve this member force. So, it is root 2 times P plus F by root 2. Then if you come to member CD, we can easily identify the direction of the member force. If you resolve this member force in the horizontal direction, you can actually identify the direction of the member force BC. And this is P plus F by root 2. Then if you come to member AD, here also you can identify the direction of the member force, and this is P plus F by root 2. Now, this reaction is P because this horizontal reaction must be balanced by the support reaction which is developed here. Now, if you take the moment of all external forces applied with respect to this point A, you can easily verify that this support reaction is P. And if you take the moment about the point B, then you can show that this reaction is effectively 0. Although we only need the member force to solve the structure. For that, we have already solved along with the direction of the member force. And to solve these structures, to find out the unknown member force F, it is better to develop a table, because for truss problem it is much easier. So we have member force. So identify the members. These are AB, BC, CD, DA, AC, and BD. Then let us identify the length of the members. So length of the member is AB is L, BC is L, CD is L, DA is L, then AC is root 2L, and BD is also root 2L. Then we have already solved member force, or let it be Ri. That was the notation we used earlier. So here we have Ri. So the member force in AB we have F by root 2. In BC we have member force P plus F by root 2. Then in CD we have again P plus F by root 2. Then DA again P plus F by root 2. Member AC has the force root 2 P plus F. And member BD that we have replaced with a force F. So now we can find out Ri square L of the member divided by AE. So let us do that. So for the first one, we have F square L divided by AE. For the second one, we have P plus F by root 2 whole square times L divided by actually twice AE. So we have a 2 here. Similarly, for the member CD, we have P plus F by root 2 whole square times L divided by twice AE. For DA, we have again P plus F by root 2 whole square L divided by twice AE. Member AC, the force is root 2P plus F whole square times L divided by twice AE. And for the last member, we have root 2 F square L divided by twice AE. We'll have a root 2 here because the length for the member AC is root 2. So we'll have root 2 L. Now, if we sum it up, we'll get the total strain energy stored in the system. Right? Okay, here we will get total strain energy stored in the system if we sum it up. Now, obviously, we need to differentiate this total strain energy, or let us write it total T with respect to F, and which is equal to 0. Now, that we can easily evaluate from this table. So, first one, if we differentiate this, we have FL by AE. Similarly, we can calculate that for each and every member, and we can add them to 0. So let us complete the task. So FL by AE for the first member. Now next three members, you see we have the same strain energy, and if we differentiate with respect to F, we get P plus F by root 2 times L divided by root 2 AE, and we have three of them, so we can multiply it with 3. Plus, for the member AC, we have root 2 P plus F times we have root 2L divided by AE. And then we'll have the last one, that is the member BD, and for that we have root 2 FL divided by AE. This is equal to 0. Now, if we solve this equation, we will get the only unknown, which is F. That we will do in a minute, but you can see we first remove one member, which is the indeterminate force that we are going to solve for this truss, and then using that force F, we have solved the complete truss, and then we find out the total strain energy stored in every member. And for truss problem, if we make a chart, that is much easier to manage because we have different member forces and we can identify the length of each and every member and the member force, and the moment we do that, we can easily find out the total strain energy, and that if we differentiate with respect to the unknown force, we can solve the problem. And before we solve, again, let me explain once more. We have the individual members with their strain energy here, and that we differentiate with respect to F. So for example, the first one, F square L by twice AE, if we differentiate with respect to F, it is FL by AE. For the second one, we have P plus F by root 2 whole square times L divided by twice AE. So if we differentiate this expression, what we have is P plus F by root 2 times L, and then F by root 2 we have to differentiate with respect to F, so that's why we have root 2 here, right? And there are three members, so we have 3 here. Now we have 2 remaining members. First one is AC, and for that you can see root 2P plus F whole square times root 2L divided by twice A. So if we differentiate this with respect to F, we have root 2P plus F times the length of this member root 2L, and then we have to differentiate F with respect to F, which is 1. And for the last member, which is BD, the strain energy is root 2 F square L divided by twice AE, and that if we differentiate with respect to F, we get root 2 FL by AE, right? And all of them, if I sum it up, is equal to 0. So let us solve this equation. So we have F L by AE plus P plus F by root 2 divided by root 2 AE times L, and we have 3 such members, plus we have root 2P plus F divided by AE, and then we also have root 2L. Plus the last one, root 2 FL by AE. So this is equal to 0. So we can cancel this AE. So the first term is FL plus we have 3 by root 2 times PL plus FL divided by root 2 plus we have root 2L times root 2P plus F plus root 2FL. This is equal to 0. So FL plus 3PL divided by root 2 plus 3FL divided by 2 plus 2PL plus root 2 FL plus root 2 FL. So we have one FL here, there, here, and there. Okay. So 5 FL by 2 plus 2 root 2 FL. This is equal to 3 by root 2 PL plus twice PL minus of that, right? Okay. So FL is equal to minus 3 by root 2 plus 2 times PL divided by 5 by 2 plus so we can cancel L. So F is minus, we have 3 plus 2 root 2 divided by root 2 times 2 divided by 5 plus 4 root 2 times P. So this is root 2 times 3 plus 2 root 2 divided by 5 plus 4 root 2 times. So we get the expression of the unknown member force for the truss in terms of P. So we have solved this complete problem, and now you have seen how we can use the theorem of Castigliano to solve the indeterminate truss problem, where we have internal indeterminacy and those member forces we can replace with an unknown force, and then using theorem of Castigliano we can solve the complete problem. So with that, let us close here. If you have any difficulty, do let us know, then we will clear your doubt. Thank you.